So in this video, I'm going to talk about free body diagrams, everything from what they are, how to draw them, and the common mistakes that people make when they're attempting to draw free body diagrams. So to start off with, free body diagrams are often abbreviated to FBD, and they can be defined as a vector diagram that shows the external loading, so both forces and moments, which are acting on a body. So I've got a few examples here of images which have been drawn from questions where you need to draw free body diagrams. And underneath, I've drawn a free body diagram corresponding to the image. So what you're going to notice in each of them is that the body of interest has been isolated from everything else that is in the picture. So for this particular example, clearly I'm interested in this bar, and it's been drawn here, as you can see. And then I've got a whole heap of different forces which are being applied onto the bar, and that's from things like the contact that it's got against the ground and the walls, and also the weight of the actual bar itself is being considered. So if we move on to this next one, what we can see is that I haven't isolated the entire system. What I've done is just taken out one part of it. All right, so this is my body of interest this time. And I've isolated it from everything else and then drawn in all these different forces which are being applied onto the bar. And these come from the fact that it's connected to other components. There's also this connection with the floor, which is now represented with a force. It had like an applied moment, all right, so that's represented here as well. And finally, we have like a force that's created from the connection to this other bar. All right, so that's another one. The last example here is a truss that I've got. So clearly what I'm interested in is the entire truss as the body. So that's what's been isolated from the system. I've got rid of these supports and I've replaced them with the equivalent reactions. The only other forces I have on the diagram are the actual applied ones, which we can see here. So each of these is an example of a free body diagram. So I've got a couple of key features that I've noted down for the free body diagrams. So one of them is that it's free, okay? That's where the free in free body comes from. So that means that the body of interest is separated or free from all of the other bodies. So that's what I talked about in terms of isolating your part of interest. Particularly for trusses, what I've done here is drawn the entire or overall structure's free body diagram. But if you wanted to, you could isolate just one of the components or one of the members out of your truss and draw the diagram just of it on its own. So it would have, this external force, the force that's from the connecting members, and so on. Okay, so it's up to you kind of what you make the focus of that diagram. All right, the other thing is that the location and direction of the loading is really important. Okay, so we need to make sure that we're applying the forces in the appropriate places and that the direction we put on the arrow makes sense with what it actually is. We're going to talk through the types of common loadings that we have for our free body diagrams in a moment. But before we get there, the last little thing I want to talk about is why do we even draw these free body diagrams? Why is it important? So I've summarized it into 3 main points. The first one is going to be visualization of what's actually happening. So by representing all the forces and loading on our structure in terms of a nice diagram, it's quite easy to see where the forces are acting and where like the reactions and things like that are coming from. As well, once we start associating values with these variables that we've defined, you're going to be able to do a quick check of whether the force is kind of balanced to what they think they should. So in the case of a structure, which is not moving in space, what we should have is the number of, or the amount of force going up, balancing against the amount of force going down. And similarly, we should have the amount of force going to the left is balancing against the amount of force going to the right. So you can do a kind of quick check of that when you filled out your diagram to make sure, yes, okay, everything looks like it should. So the next reason that we have is keeping track of what forces you're accounting for, including their direction. So with respect to like keeping track of the forces you're accounting for, obviously you need to make assumptions when you draw this free body diagram. So you may be assuming that, say, friction is acting in your scenario. You may be assuming it's not. You might be assuming that the weight of the body that you're drawing is not particularly significant in the scenario. I would make that assumption here, it looks like, because I haven't got a weight force drawn on it. So what we're doing is just making sure we're keeping track of which things we're considering and which things we're not in terms of the assumptions. With respect to this direction part, Sometimes we need to make a guess as to what direction a force is actually acting, and it's really good to mark that on the diagram what your assumption is, especially if you need to make an assumption for more than one, because sometimes we can get these variables or unknowns mixed up in the equation, and it can be difficult to see what is actually going on. You mark in what your assumption was. So for example, I'm assuming that FCD is going to the right. You're going to know if you get a negative answer out at the end that actually your assumption was wrong and it's going the other way. But if you don't mark it in your initial diagram, it's going to be harder to go back and see what you've actually got as your outcome. So the last thing is about communication. So if you do a whole heap of analysis of a particular structure or body, you're going to probably need to communicate that to other people. And a free body diagram is an excellent way of communicating that. The other thing is, even if you remember today what you made in terms of assumptions in your analysis and what directions and things like that you put in for the various different loadings, if you come back to this in like a month or 2 months' time, are you really going to remember that level of detail? So yeah, this one is really, really important. Whatever analysis you do, you need to be able to communicate that to other people as well as yourself if you ever need to go back and review what you've done. So I've made this last little point on the end. So by going directly to the governing equations, so this would be like sum of forces is equal to mass times acceleration, or sum of moments is equal to 0 if it's a structure that's not moving. And calculations for steps in the analysis procedure, we're going to be omitting the problem statement, the diagram, and the assumptions. And I know sometimes that it does seem tedious having to draw these diagrams and write out your problem and what assumptions you're making when you have very, very simple questions and very short questions. But in the long run, if you're doing an analysis which is of a large structure that might involve multiple bodies and many, many steps in order to get to an answer, it's going to be really, really important that you go through these processes. And that's why in every single question that I'm going to do that uses, say, sum of forces equals mass times acceleration as an equation, I will be drawing the diagram associated with that equation. So I've got a list of, I think, 4 common errors that people make and a bit of an example of what that might look like. So the first one mistake is that the body that is being considered is not free of the other things that were attached to it. So in the example here, this is the truss one. What we can see is someone's tried to draw a diagram of the overall truss, and we can still see the supports are pictured in this diagram. So that's what the mistake is, all right? It shouldn't be supports in this diagram whatsoever, because we've replaced the support with the AX, AY, and BY forces. So technically, if I make a really kind of crude picture of this, right, that's meant to be my truss or whatever, what we should have is just the forces drawn directly onto the truss itself, all right, no little triangles representing the roller and the pin support whatsoever. So that would be my correct diagram. The next one here is incorrect simplification of the support. So again, we've got our truss, and what we can see here is we've got an AY applied, but actually at A here, it's a pin support. All right, so this is incorrect. We should have both a horizontal and a vertical force acting at a pin. Up here, this one's okay because that one's a roller, it's on little wheels, so we do have the one force there, which is correct. All right, the next one, which happens a lot when people do truss analysis, is that the arrows do not have the correct directions. So what I've done here is I'm looking at a free body diagram of joint A, which is this one down the bottom, and I guess I've kind of labeled some of the points as well. So this one is going to be called B, and this one is going to be called C. And what I've done is I've picked apart the free body diagram of what's happening just at that joint, all right, that little dot. So it's got AX and AY, all right, which are the horizontal and vertical forces acting on that joint from the support to the ground. And then we've got these forces FAB and FAC, which are corresponding to the members that we see. Now, at the moment, these don't have any arrows drawn on them, which is incorrect, all right? A free body diagram, it's a vector diagram, so we need directions, all right? Otherwise, it's not vectors. So we need to take a guess, all right? So I'll just guess these directions for those arrows, and then that makes it a correct free body diagram. Remember that when we do our calculations, we'll figure out whether this was the correct direction or not. If it comes out negative, we know, okay, we just have to flip it over. It was in the opposite direction. Alright, so the last error is just people putting forces in the incorrect location or in the wrong direction for each of them. So I've just got an example here where we've got a block that appears to be sliding down a ramp, and when we look over at the free body diagram that's been drawn, the weight looks alright because it's acting through the center of gravity. The normal force looks good because it's applied perpendicular to the contacting surface. But what we see is this friction force is not opposing the direction of motion. It's in the wrong way round. So technically, this should be going back up the ramp. It's just important that you maintain your awareness of what assumptions that you're making, i.e. this is moving down the ramp, so therefore your forces and things like that align with those assumptions. So that's pretty much all there is in terms of this video, and there is other ones looking at what, say, roller, pin, and fixed supports actually look like in terms of their reactions and so on, that I'd recommend you have a look at if you're unfamiliar with that. Otherwise, that's all there is, and see you in another video.